We have reached the end of chapter 13. Sadly, get your Kleenex box out. We're going to look here at systems that have a really small equilibrium constant. And we've kind of referred to this concept in the past that K is a measure of products over reactants. If your K value is really large, then we'd say that the system favors the products. And sometimes when K values get really large, we might even say that the reaction goes to completion, that we have primarily products, and if there are any reactants, it's almost insignificant. Systems that have a small K value are the opposite. If they proceed, it's not by much at all. Yes, they might be going forward, but most of our particles are still the reactants. Maybe an example might be something like a decomposition that's highly endothermic. You need a really substantial energy source to get this thing going. So will it decompose? Maybe to a small extent. But that's kind of what we're going to look at here. A system that has a small equilibrium constant, something that goes forward but not by much. And by small K value, we're talking like maybe 10 to the negative something power. So in this example here, our equilibrium constant is 1.6 times 10 to the negative fifth. I'd call that small. I'd call that really small. Something times 10 to the negative whatever power. Okay, so let's get this thing started. Let's approach this like any other equilibrium system. I know I'm going to want an ice table. So we're going to write our equation. 2NOCl. We're going to form 2 nitrogen monoxide and a chlorine. And we'll ICE. And we'll start this off with our initial concentrations. What do we have here? At 35 degrees, the equilibrium constant is 1.6 times 10 to the negative fifth. In an experiment in which 1 mole of NOCl is placed in a 2-liter flask, what are the equilibrium concentrations? Okay, so be careful of this. It's 1 mole in a 2-liter flask, and when you plug numbers into an ice table, your options are pressure, atmospheres, torr, millimeters mercury, or concentration, like moles per liter or molarity. In this case, then, I want to plug it in as 0.50 moles per liter. There is no mention of the products, so we're going to say they're 0. Okay, excellent. We do not need to calculate Q in this case. At equilibrium, there can be no zeros. This thing has to go forward and reverse. So if I see zeros, I know that I'm shifting toward the 0. So we're going to shift forward. There cannot be anything at 0 when we have reached equilibrium. Okay, so great. We have to shift forward, but we are given no indication as to how far forward we need to shift. I know the equilibrium constant, but I don't know any of the other equilibrium conditions. So let's plug it in as x. We know we're shifting forward. We're going to shift by the ratio in the balanced equation. So the reactants are going to go down. We're going to call this minus 2x. My products will increase plus 2x plus x. We have to change by the ratio in the balanced equation. That's a common mistake people will forget. And then they'll get it back and they'll slap themselves in the face. I knew that. So just keep your eyes open for the ratio in the balanced equation. And then at equilibrium, this would be 0.5 minus 2x. This would just be 2x and x. So again, this seems really simple, right? Let's just solve it for x and be done with it. I do know the K value. I do know K is 1.6 times 10 to the negative fifth. That equals products over reactants. I'm going to have 2x. And I still need to square it. When I set up my equilibrium expression, I still need to square it because of that ratio. This will just be x to the first all over 0.50 minus 2x. And I still need to square that too. All right, so let's just solve this for x piece of cake, right? Now we've had some things that kind of look similar where like there was something squared on the top, something squared on the bottom, and we could just take the square root of both sides, and that really simplified our algebra. I can't do that here. I've got the 2x squared on the top, but it's times x. So I can't really like take the square root of both sides. Ew. Okay, so what are our options then? Do I have to FOIL out the denominator? And like, do I really have to like then collect like terms? And I think I'm going to need the quadratic then. Which we did in the last video. You can solve it that way. But we also mentioned that on the AP test, you do not need a graphing calculator. You don't need a programmable calculator with the quadratic solver. You don't need any of that. You just need a scientific calculator. Here's why. Often, when you get a situation like this, where you're like, oh no, in order to solve for x, I'm going to need to FOIL and solve the quadratic. Look at your k value. If your k value is small, and by small we mean 10 to the negative something power, you can do a little shortcut. Here's how it works. Since k is small, we're going forward, but we must not be going forward by much. So this x quantity, whatever it is, it's small. It's probably really small. Because products over reactants, my k is really small. I must have primarily reactant and not a lot of product. So if this x thing is small, then here when I'm subtracting 2x, that must be a small quantity. That must be small. Because the equilibrium constant ends up being so small. What if this x value were to be so small that it was almost insignificant? Like, wouldn't it make your math a little quicker if you could just get rid of that thing? Like, yeah, we're going to subtract a small amount. Yes, some of the reactant will get consumed, but it's not a lot. What if I just got rid of that? I mean, obviously you can't get rid of all your x's. You got to solve for something. But this whole like minus 2x thing, like it's going to be small. Could we just get rid of that? And now watch what it does to my math. Now I do still need to simplify this. Like I do need to say, let's go, this I'm going to still need to square. This I'm going to need to square. But could I simplify this and say like 1.6 times 10 to the negative fifth equals, on the top, could I go 4x cubed over 0.25? And then I could kind of cross multiply and simplify that out and say like 4.0 times 10 to the negative sixth equals 4x cubed. Okay, and so now I could simplify this further and maybe say like 1.0 times 10 to the negative sixth equals x cubed. And I haven't hit this button in my calculator for a while. But what if we took the cube root of each side? Oh, fun. And we said x equals cubed root 1.0 times 10 to the negative sixth, 0.01. That made my math a lot easier. I mean, I still use my calculator a little bit. But I didn't have to solve this thing for the quadratic and all that fun stuff. I mean, which is fun, but this is a little quicker. Okay, so now we have an x value, and then I would just go back and plug x in to my equilibrium conditions. Yikes. And we would say at equilibrium. At at equilibrium, my NOCl is 0.5 minus 2x. 0.5 minus 0.02 would be 0.48 moles per liter. My nitrogen monoxide would be 2x, 0.02, I'll say 020, we'll go 2 sig figs, moles per liter. And my chlorine is x, 0.01 moles per liter. There we are, not bad, huh? Okay, are you still a little concerned with the fact that I just crossed off that minus 2x? You probably see how it did make our calculations a little easier. But is it really okay to do that? You can just get rid of the minus 2x? Yes. It's called the 5% rule. Remember that. The 5% rule is a good thing. We're going to use it a ton. I mean, right now it seems like, a little strange, but this 5% rule will just become ingrained in your brain. You'll love it. Here's what happens. So I made an assumption. When I did my calculations, I just assumed that the NOCl was 0.5. I assumed that the whole minus 2x thing was so small that maybe it's kind of insignificant. Yes, I'm going to consume some of my reactant, but not much. So I just got rid of it. Now, once I actually calculated that concentration, the calculated amount of NOCl was 0.48 moles per liter. Here's the 5% rule. So you get rid of any minus or plus x. It's going to save yourself time when doing the math. And you can do this as long as k is small. Because again, then x must be really small. If I'm shifting this thing forward, it's not by much. So let's just get rid of that minus x or minus 2x, whatever it might be. Then you do a quick check. And you do want to check this. I assumed the concentration was 0.5 when I did my calculation. Once I actually calculated them, the concentration, I get 0.48. These guys differ. I should say they must differ by less than 5%. If these differ by less than 5%, your assumption was valid. And it really does just save you a lot of time and energy when doing the calculation. These guys differ. If I plug this in my calculator, here they differ by about 4%. So that was a fair assumption. So I usually do this. When I list my final answer, I'll just say 5% rule, check. That's how I acknowledge the fact that my assumption was valid. I had the original setup, but when I did the math, I did not include that minus 2x because of the 5% rule. X is small, whatever it is. It ended up being small, 0.01. It was so small that my assumption differed by my calculated amount by less than 5%. So I usually do this, I do a little check. Sometimes it's obvious where you're like, oh yeah, I mean, they're like almost the same thing. You don't even have to check. But in this case, I did, just to make sure. And yes, they differed by 4%. That assumption was fair. It's called the 5% rule. You will use this a lot, especially in some of the next couple chapters. You're going to love it.